today we are going to start the last chapter of the electrical measurement parts. Okay. And this will have several miscellaneous topics. One of them is magnetic measurement, where basically we will measure the flux density or field intensity of a magnetic field. And here we will see two small topics. One is measurement of flux density, magnetic flux density, in a core with ballistic galvanometer, and the second thing we will study is a Hall effect sensor. So, let us start with this one, that is flux density measurement with a ballistic galvanometer. So, let us recall what a ballistic galvanometer is. We have studied this I think in our first week. So, a ballistic galvanometer can measure the charge, the total charge flown during an impulse or impulsive current. Okay. So, if we have a very short duration current, but of high enough magnitude, but very short duration, the current lasts for very short duration, then some charge will flow within that duration, and that charge can be measured with a ballistic galvanometer. Just recall what we have studied, go back to your our first week. So, if we connect the ballistic galvanometer in series with this impulsive current, then the pointer of the galvanometer will get a throw, will start to oscillate. Okay. The moment the current passes, the pointer will be thrown like this, it will be ticked and it will start to oscillate. The ballistic galvanometer does not have much friction, ideally no friction at all, and the amplitude of this oscillation, that means from here to here, this amplitude is proportional to the charge flown within that small time. Okay. So, please revise that if you have forgotten. Now, suppose we have a magnetic material and we want to estimate its say BH characteristic. Okay. So, what do we have to do? So, we will first make say a small toroidal ring, a circular ring with that material which we want to test. So, this is a magnetic material under test, and then we will wound the coil with some number of turns, and then what we will do, we can do many different things. One possibility is take a battery, connect an ammeter, okay, and take a switch. The switch is normally closed, NC normally closed. So, initially closed, and then we will open it suddenly. So, opened suddenly. And when the switch is closed, we can measure this current I using this ammeter, and when this is opened suddenly, this I will become 0 immediately, right. So, therefore, the current here will become 0 instantaneously when we open this switch. Okay. Now, if we change this current suddenly, then the flux, okay. So, the flux in this code is like this. When the current is flowing, this flux phi will also become 0 very soon, very quickly, as soon as we make this I equal to 0 by opening this switch. So, there will be a quick change of the flux. Now, what we will do? We will take a second coil. This will be owned here. This is like the secondary. This is also called the surge coil. You can call it secondary, and we will connect a ballistic galvanometer here. Now, if when I is changed, when I is stopped suddenly, then phi is also becomes 0, becomes also 0 suddenly. So, there will be a change of flux and a change of flux linkage of the secondary coil. So, if this number of turns is N2, okay, then the change of flux linkage of secondary or surge coil is equal to how much? So, this will be initial flux linkage minus final flux linkage. Initial flux linkage is phi times N2 multiplied by minus 0, because final flux is 0. Okay. So, this is phi N2, and this we can write as B A N2. What is B? B is the flux density. What is A? A is the cross sectional area of this core. So, A is cross sectional area, and B is flux density, and we say want to measure this B. Okay. The goal of the experiment is to measure, to estimate this flux density B that was present when this current was flowing, when this current I was flowing. Okay. So, we want to estimate this B. How we will do this? We will do that using this galvanometer. How? Okay. Okay. So, the change of flux linkage, call it d psi, is given by this quantity. And if we assume, okay, so approximately, so let us do this analysis first approximately for ease of understanding, then if time permits we will do it more accurately. So, approximate analysis say flux linkage is changed from this value BAN2 to 0 in time, very small time dt. Okay. Then the rate of change of psi flux linkage is this d psi dt, where d psi is nothing but BAN2 divided by dt or delta t. Okay, you can call it delta t if you like. So, let us call that delta t. Let me call everything delta, okay, divided by delta t. This is the rate of change of flux linkage. So, how much EMF will be generated in the secondary search coil? So, EMF induced in secondary will be equal to this rate of change of flux linkage according to Faraday's law. So, that is BAN2 by dt. So, this is equal to E. Now, if this is E and say the resistance of the secondary side is equal to R, say, then secondary current will be how much? Voltage by resistance I, this will be EMF by resistance. Now, E is equal to BAN2 by delta t and divided by R. So, this is the current. Now, this current will flow only as long as this EMF is there, that means only as long as this flux linkage is changing, and the flux linkage changes within a time of delta t, approximately assuming. Okay. So, then the total charge flown will be total charge flown in delta t time this will be equal to I delta t, and this will be equal to I is this BAN2 by R, delta t and delta t will cancel. So, this is the total charge. Now, this will be measured. So, this quantity this is measured by the ballistic galvanometer. This charge is measured by ballistic galvanometer. Okay. So, we observe this. So, this is known. So, this is known, call this equal to Q measured, and therefore, we can estimate B as Q R by A N2. Q is measured, R can be known or measured, A is known, N2 is known. So, B can be estimated. So, this way we can estimate B. So, this way we can estimate B for a particular value of this primary current I. So, this way, okay. So, this way we have measured B for the MMF produced by the primary current. What is how much is that? If this current is I and this is N1, then MMF was, or H, okay, so the MMF was I times N1 for the MMF equal to I times N1, or H is equal to what? H is equal to MMF I N1 divided by L. What is L? L is this length, mean length of the core, this length. Okay. This is the mean length of core. Now, I is observed, N1 is known, this mean length can also be known. So, H is known. So, therefore, H is known, B is measured, and this way we can measure B for different values of H by selecting different initial currents here, and then we can plot a curve for different values of H. We can plot the values of B and we can get a BH curve. We can also sometimes do a slight variant of this experiment. So, which is like this. So, a small variation. So, what we can do is this, we can connect a commutator . Okay, I am not good at drawing this commutator. What is this commutator? The commutator means we will say initially initially we will have this connected like this. Okay. Then current I, this current I is flowing in this direction. Okay. So, this is the initial situation, and then we will suddenly change this switch position like this. This is the final position. Then this current I will now flow in the opposite direction. Okay. So, the current changes from I to minus I. So, total change is double. So, flux will also change from phi to minus phi. So, flux linkage, change in flux linkage d psi will be double. Okay. So, it will be, so previously it was how much? BAN2, right. This is d psi BAN2. Now, it will become double 2BA(2), and then you can do the same calculation. Okay. But now, you have more flux change. So, definitely more EMF will be created. So, you will have more current and more charge flow through this. So, the sensitivity of the measurement is increased. Okay. So, that is how we can measure flux density. Thank you.